All right, next we are going to have Dr. Ben Lee come to the podium. Dr. Lee is a PGY2 integrative vascular resident at the University of Toronto and enrolled in the surgeon scientist training program and pursuing a PhD in machine learning. So, welcome, Dr. Lee.
Thanks, Dr. Hazelburn. I'm really excited to share with you our work on using machine learning to predict outcomes following carotid endarterectomy. So carotid artery stenosis, as you know, is responsible for 1/3 of ischemic strokes, and that's a leading cause of mortality and morbidity worldwide. Carotid endarterectomy, or CEA, involves surgical removal of the plaque. However, the procedure carries significant risks, including a perioperative stroke or death rate over 10% in the highest risk patients. Therefore, accurate prediction of outcomes following CEA is critical for guiding clinical decision-making. Currently, there are no standardized tools to predict outcomes following CEA. A recent systematic review of existing models demonstrated significant methodologic limitations, incomplete reporting, and inadequate performance. Furthermore, traditional tools use modeling techniques that require manual input of clinical variables, and this deters routine use in busy medical settings. Therefore, there's an important need to develop better and more practical risk prediction tools for patients undergoing CEA. Machine learning, or ML, is a rapidly advancing field that enables computer technology to learn from data and make predictions. Supervised learning is a subset of ML that leverages advanced analytics to model complex relationships between inputs, such as a patient's characteristics, and outputs, such as their clinical outcomes. And this technology has been driven by the explosion of electronic information combined with increasing computational power. Our goal was to develop an automated ML algorithm that accurately predicts 1-year stroke or death following CEA at the pre, intra, and postoperative stages. We used the VQI database to identify all patients underwent CEA between 2003 and 2022. Patients with unreported symptom status were excluded. The predictor variables, or the input features used to train the ML models, were divided into the pre, intra, and postoperative stages. So we included 43 preoperative features: demographics, comorbidities, functional status, investigations, medications, anatomy, and clinical presentation. There were 21 intraoperative features, so type of anesthesia, surgical technique, intraoperative hemodynamics, procedure time, and the need for surgical reexploration. And 7 postoperative features, mainly in-hospital complications and length of stay, so whatever was available through the VQI. The primary outcome was stroke or death at 1 year following CEA. And we defined stroke as neurologic deficits persisting for over 24 hours in the ipsilateral or contralateral cerebrovascular territory. And death was defined as all-cause mortality. We trained 6 ML models: XGBoost, random forest, naive Bayes classifier, support vector machine, artificial neural network, and logistic regression. The reason we chose these is because they demonstrate the best performance for predicting surgical outcomes in the literature. We split our data into 70% training and 30% test sets, and we performed 10-fold cross-validation and grid search to find optimal model hyperparameters. We then evaluated the models on unseen test set data and ranked them based on performance metrics. So the models were first compared at the preoperative stage because predictions at this time point are the most important in guiding a patient's care, such as determining whether to proceed with surgery or not. And once the best performing preoperative model was identified, we further trained it using intra and postoperative data. And the reason we built models in this fashion is to allow clinicians to understand a patient's risk throughout their surgical course. The primary model evaluation metric was AUROC, and the secondary performance metrics were accuracy, sensitivity, specificity, positive predictive value, and negative predictive value. We further assessed model robustness using calibration plots and Breer scores. And here's what we found. Overall, we included 166,000 patients, and 4.7% had the primary outcome of stroke or death at 1 year. Of the patients who had an event, 1.4% developed a stroke and 3.3% died. The median time to event was 90 days, and the mean follow-up time was 14 months. This table shows model performance on test set data for predicting 1 year stroke or death following CEA at the preoperative stage. So we trained 6 ML models. The best performing one was XGBoost, and that achieved an AUROC of 0.9, accuracy of 0.82, sensitivity of 0.82, specificity of 0.83, PPV of 0.83, and NPV of 0.81. You can see that this performed significantly better than traditional logistic regression, which only achieved an AUROC of 0.65. This is the ROC curve for predicting 1 year stroke or death following CEA using our best performing XGBoost model, again at the pre, intra, and postoperative stages. So you can see excellent performance throughout with AUROCs at or above 0.9. There were no significant differences between our pre- and the intraoperative models, and this suggests that a lot of the predictive power lies with the preoperative variables. When we added in postoperative variables, so in-hospital complications, this improved performance. And this made sense because patients who have in-hospital complications are more likely to have worse one-year outcomes. These are our calibration plots for the XGBoost model, again at the pre, intra, and postoperative stages. On the x-axis are the predicted event probabilities, and on the y-axis are the observed event probabilities. The red line shows the performance of the ideal model, while the blue line shows the performance of our model. You can see generally there's good alignment between the red line and the blue line, meaning that our model is well calibrated. And this is further demonstrated by the Breer scores, which suggest excellent agreement between what is predicted and observed in terms of event probabilities. These are the top 10 predictors of one-year stroke or death in our model, the most important of which was in-hospital MI. And this made sense because patients who have major in-hospital complications are more likely to have worse one-year outcomes. Other important predictors were preoperative dialysis, the need for surgical reexploration, primary major amputation, among others. And when we looked at these top 10 predictors, they made sense to us clinically, meaning that our model was explainable. So in conclusion, we used a large granular data set of 166,000 patients from VQI to develop a robust ML model that accurately predicts one-year stroke or death following CEA. Our models can be applied at the pre, intra, and post-operative stages to guide clinical decision-making and help mitigate the risk of adverse outcomes. And with the advantages of continuous learning and automation, the ML algorithms here have potential for important utility in the care of patients with carotid artery stenosis. We've made our tool publicly available along with the programming code. And this work was recently published in the JVS, and you can access the full text here. I'd like to thank the SVS VQI FIT program, the Canadian Institutes of Health Research, Ontario Ministry of Health, and the PSI Foundation for supporting this work. Thanks for your time.
That was a really nice, nicely done presentation and a really elegant example of kind of the power of machine learning. I love that you included the QR code there because I was going to ask you how do we use this ourselves. Have you, I guess, as we think about all of these tools in the clinic, is this something that you think, how do we get the buy-in from at the clinic? So you have a great model, you show how much better it is than our traditional logistic regression. How do we get surgeons to use it preoperatively?
Yeah, thanks, Dr. Osborne. So I think one of the major limitations right now with current models is that clinicians have to sit there and manually input variables. Like, for example, with the NISC risk calculator, there's about 20 variables we have to input. And even with the current SVS VQI calculators, you need to manually input variables. And how we've developed this tool is it automatically extracts patient data from the VQI database and comes up with a risk prediction. And so I think with this automation, and with the good performance, I think this will help get buy-in from clinicians in terms of using this tool.
Yeah, so to expand on that, another thing is this can be driven by, by the EHR and comparing it and then be turned into a clinical decision support or a best practice advisory, which would be like, hey, your patient had a, had this, you may, their pre-procedural risk may look like this. So 2 other comments. Did you take a look at using a tree-augmented Bayes? Because naive Bayes isn't very far off from a logistic regression. Tree-augmented Bayes, when we looked at something similar, we saw a significant upstep in accuracy. And the other technique is K-nearest-neighbor. Also gave us, we ended up with we found some very interesting data in our clustering that I still can't completely explain clinically. But so there's clearly some unobserved stuff that we, that is hinted at by the K-nearest-neighbor. So.
Yeah, absolutely. I think there are tons of different models we can try, and I think this is just, I think, a starting point. We tested 6 ML models, and we chose them because we thought that these would perform well. But you mentioned 2 other ones, and I think I think this begins a conversation for how can we make better risk prediction tools.
Thank you. All right, great.